Hi, everyone. My name is Jay Singh, and I will be your host for this NASA Ames Technology Transfer Program webinar on the various newly patented technologies from NASA Ames Research Center. The webinar will be structured in a lightning talk format. The presenter will have 10 minutes to present their technologies and then 5 minutes for Q&A. Before we get started, just wanted to mention the Technology Transfer Program has over 1,000 patented technologies across the entire agency and 100 different technologies at Ames available for the public to license. I'd also like to point out that your microphones will be muted throughout the session. So if you have any questions, please type them into the Q&A box and we'll answer them during the Q&A session at the end of each presentation. So at this point, I'm going to hand it over to our first presenter, Sarah. Sarah, take it away.
Great. Okay. Let me share my screen. All right. Hello, everyone. My name's Sarah D'Souza. I'm an aerospace flight systems engineer with a background in guidance and control for entry spacecraft. The title of our work on this patented technology is called Aerospace Vehicle Entry Flight Path Control. Just to give you a little bit of a technology overview, the system really, or the patented technology is really focused on exploiting the dihedral effect on a spacecraft to control bank angle of the vehicle by modulating side slip. So the closed loop control system essentially includes an outer loop for producing a side slip angle command to induce a roll moment through the dihedral effect, and then an inner loop for taking the side slip command and possibly an angle of attack command to produce control inputs for the flight path hardware controls. Our patent also includes multiple different flight control hardware configurations or systems that we developed specifically for integration into a deployable entry vehicle. So we looked at flaps, moving masses, and reaction control system. Our goal was to first find feasible guidance and control methodologies with the best fidelity possible. And we didn't want to rely on heritage concepts and codes, so we could develop new technology. So a lot of the spacecraft world is really sort of rooted in capsule shapes and RCS as the primary means of control for the entry descent phases of flight. So we really wanted to focus on, let's not rely so heavily on heritage and see what we can come up with. And the result was the development of algorithms and design processes that are not specific to a deployable entry vehicle, but can be applied to other configurations as well. So in the top right, I have a graphic of our various innovations that we developed through this work. So the first one is, in order to even get these simulations running and conducting these feasible system studies, we had to develop aerodynamic and aerothermodynamic analyses for morphing geometries. And the reason we had to implement that is, for the flap control system design, you'll see that the configuration that, or the shape that is exposed to the flow will change depending on the flap deflections. So, so what we had to do was use CART 3D and then develop a methodology by which we could run a subset of configurations and then interpolate through them to capture the aerodynamics and aerothermodynamics on the flaps. The next graphic documents the dual mode guidance. So as I said, we wanted to be, agnostic to type of guidance methodologies and types of control hardware. So we ensured that we had a guidance method that you could do bank control for coupling the downrange and cross range control, or you could do an alpha beta control, which allows you to decouple the control on your downrange and the control on your cross range. And the two trajectories there that you see in the plot with the ground track really kind of give an example of how these perform for our given flap control configuration. On the right is the control system that we developed to be able to handle the dihedral effect from the vehicle. So what I neglected to mention in the beginning is we started with an asymmetrical configuration for the adaptive vehicle or the mechanically deployed spacecraft. So you'll see that the ribs on the bottom side here of the vehicle are longer than the ribs on this side of the vehicle. And so that essentially helps the vehicle generate some lift to be able to do the entry descent guidance part of the problem. But by making it asymmetrical in those directions, you essentially end up with a dihedral effect on the vehicle. So, and that dihedral effect essentially causes a roll instability. So what we decided was, well, if we know that we're going to produce a roll moment when we try to yaw the vehicle, let's leverage that and leverage that by taking the side slip command and leveraging that roll moment to do the bank commanding, since bank commands are a combination of roll and yaw. So that right graphic is our control system and is part of the patented technologies that can be licensed. And then we put together a sort of integrated system with all of these codes to do, control system prototyping, and then by the end, essentially do integrated hardware studies to ensure that we had feasible designs for any given guidance and control system. So the bottom right shows you the different systems that we looked at, the flap control system, mass movement, and the reaction control system. And what we found was the flap control system had very much, a much better maneuverability than the RCS control system, whereas the mass control system just didn't perform as well. It was a lot of mass for not a lot of maneuverability added to the vehicle. So, and then for the reaction control system, you'll see one of the reasons RCS, which is heritage, is a major challenge for deployable entry vehicles is because of the foldable nature of the system, and you can't really or there's a challenge with the fuel lines going to the thrusters and then having to fold those fuel lines. So there's a complexity in how you build it. So we came up with a configuration, but the complexity and the maneuverability being less than the flap control system really down selected it out of our control space, our design space. But it's still a viable option for development. And that is also these designs are also under our patented technologies. So in terms of benefits, we advanced our methods for controllability of vehicles with dihedral, so you can assess different types of control effectors as well in our control system. And we provide a platform to achieve solid feasibility studies that are not back of the envelope. So one of the other aspects that we strive for is not simplifying the problem too much that you don't get an idea of just how feasible the system can perform. So, but also not so much fidelity that you can't model it in time and go through your design cycles. So that was a key feature also of our work as well. So that's the technology that I wanted to preview with all of you today. I'm happy to take questions now.
Yeah, thank you. That was really great. If anyone has any questions, please just put them in the chat, and I can ask them for you. While people are typing them in, I had a quick question. So how long did something like this take to develop from kind of the idea to where you got it working into something that you could be like, hey, industry can use this and run with it?
Yeah, so 3 years, it took us about 3 years to get the system designed, implemented, and then run and published. And it took us about, I'm going to say, 6 years before it was patented. So the patent process did add a length of time to it. But essentially, it took us about 3 years of dedicated effort. And I mean, it was our full-time job.
And with that, so would if this was to be transferred to a private company, how long do you think, if they had some support from within NASA or just by themselves, how long do you think it would take them to kind of deploy this and be able to run with it?
Oh, I think they could do it in a year.
Okay,
a
great.
year. Yeah, absolutely. So one of the things that we made sure to do for all of the work we did was baseline our algorithms and make sure that we had test cases that you could verify against, and took copious notes on our development. So we are poised to be able to assist and help folks get this technology up and running. I don't see a lot of lead times to do that.
Got it. Yeah, so thank you. I appreciate the presentation. It was very knowledgeable.
Yeah, no problem.
Thanks so much. All right, and let's see. So we just had one quick question, last question. Was the moving mass parasite mass?
I don't know if I've heard that term before, but I'm going to assume that it means its only value was to the control system and it had no other no other value. And I would say yes. Of all the options we looked at, this was just thrown away pretty early because there wasn't a lot of value to the maneuverability or the ability to control, and it just took a lot of mass to even get some kind of movement in the CG to control the vehicle.
Got it. And then we just have time for one last question, and then the other ones that we're not able to get to, we'll follow up. The question is, for the control system, was the prototyping made in 3 years from kind of start to finish of it?
So we were not able to build the whole vehicle, but what we did do is build a prototype of the flap connected to our control system, put the GNC on a Raspberry Pi, and fed it commands to see how fast we could actually move. Like we did tests, right? We did analysis for the pressure that we had, what kind of a motor would we need, or for the loads, what kind of a motor would we need to actually move these flaps. So we did build a small sort of flap prototype to just verify that the frequencies that we were operating the GNC at and the trajectory we wanted to run, we could operate the flap. And then we also ran our GNC on a Raspberry Pi too, sort of as a separate effort to see how it did integrated with like onboard guidance and control flight software.
Got it. Awesome. Thank you so much. Appreciate it.
No problem. Thanks, everyone.
And our next presenter will be Lee, and he will be talking about his oculometric testing for detecting / characterizing mild neural impairment. Take it away, Lee.
Can everybody see my slides now?
Yes, looks great.
Okay, so good morning, everybody. I'm going to talk to you about something a little bit different than the last talk you heard about. This is basically a human performance biomedical technology with potential applications not only in space but in earthbound activities. I'm going, whoops, wow, that went fast. I'm going to focus not on the description of the actual technology, because that would take much more than 10 minutes. I'm going to focus on a few examples of validation studies showing what this technology can do and how it can be applied. And I want to emphasize up front that these validation studies were done in collaboration with folks at Stanford in the medical school, in the ophthalmology department, Dr. Leung, and I also have collaborators at JSC, and in the fatigue lab here at Ames. My lab is the visual motor control lab, but this was a group effort to validate this technology. So I'm going to give you the bottom line up front. For a very long time, people have known that eye movements can be used for medical applications. This has been known for more than 100 years, so that's not new. And a matter of fact, prior to the advent of modern imaging in the 80s, eye movements were used to diagnose the location of brain tumors in the brainstem and in cerebellum in particular. But the big difference is that it was to diagnose rather gross, obvious medical problems, and it focused largely on visual and vestibular reflexive kinds of things. And it was very successful, but then it was displaced by all the modern imaging, which could locate these tumors much more precisely. But what COBRA, the technology I'm going to talk about, does is it takes this to a completely different level, where instead of being able to detect and characterize and understand very large pathologies where your eye movements are doing extremely bizarre things and you make inferences from that, this is looking at largely normal eye movements, but looking at very subtle quantitative differences in those eye movements to look at very subtle impairments caused by mild stressors or other factors that could be interfering with your optimal performance. And so it's about preclinical mild impairment being detected in a reliable way. And the other important thing to point out is it's easy to say theoretically that you can do something. It's another thing to show that the mechanism provides reliable data that is sensitive and reliable. And so that is something that we did a number of studies on this, showing that we have quite reliable data, that there are very small learning effects and only a subset of the measures that you get. And so you can use this to detect very small changes in performance, both within a subject and across subjects. And I'm going to focus today on 3 examples of how COBRA can be used to detect and characterize these mild impairments. So once again, I wanted to give credit to where credit is due to the collaborators in my lab and in Aaron Flynn's lab and at Stanford and at JSC. So I'm going to quickly say what the technology consists of, but I could spend a lot more time on the details of why each one of the details is important. But it is effectively a small desktop system that has hardware for a camera here, an infrared camera, an infrared light source, a high-speed display. So there's some hardware here, and there's a task that subjects are asked to perform, and we collect data over a 5 to 10 minute period. We've gotten it down to 5 minutes reliably now. We randomize the stimuli so that we're forcing subjects to behave in a very repeatable way instead of letting them develop, individualized strategies. Strategies don't work. Everything is randomized. You just have to watch the target and do the best you can. The task is basically to have you fixate the center of the screen at a random time, so you don't know when the target's going to start to move. It's going to jump in a whole range of possible areas around the clock, so you don't know where it's going to jump, and it's going to start moving in a random direction that you can't anticipate, and it only moves for about a second, and then it's gone. And you're asked to track that as best you can. The last part of the patent is that we have a very specialized analysis routines that analyze the eye movement data that we get to extract not just a single piece of information, but 20 pieces of largely independent information that are telling you things about your function in different parts of the brain. So I'm not going to go over these in detail, but there are 20 metrics here. There are pursuit metrics, which is one type of eye movement that is engaged here, that is largely a cortical system. You have another more primitive eye movement system that is also engaged in this tracking task, which is the saccadic system. That is largely implemented by the midbrain and brainstem. There are higher order motion processing parameters that come out of this. It shows you some of the highest level cortical processing going on. There's fixational control that is looking at cerebellar function, and the pupillary light reflex is a separate brainstem visual system that is also important. So as you can see, these 20 parameters are telling you different things about what's happening in different parts of your brain. So one of the most reliable ways of causing a reversible and safe neural impairment that we all have some subjective experience with, or maybe not all, but many of us, is alcohol. And so we did an alcohol study where we generated dose response curves and measured how well these 20 metrics that come out of your eye movement measures tell you about your function. And this shows you a plot of 4 of the 20 parameters. This has all been peer reviewed and published and rigorously statistically tested. But what this is deviation from your baseline. So these are within subject baselines where each subject serves as their own control. And it's a dose response. Well, how deviated are you from your normal as a function of blood alcohol level? All of the data points you see here are underneath the legal limit of 0.08 in California and in most states. And what you can see here is you see a clear linear trend of impairment across these 4 different metrics. The impairment is not small. These are like 10%, 20% reduction in your gains, 10 millisecond delays in your responses, 20 to 30% reduction in your initial accelerations. So these are not subtle effects. And I want to point out the X scale here is in blood alcohol levels. And so basically 0.04 is approximately 1 drink. 0.02 is a half a drink. And what you can see in those red symbols here is that there are significant deviations from people's baselines at less than half a drink. So this is picking up incredibly small deviations from their performance. And so that is, I think the take-home message here is you can detect things that they subjectively don't even know is going on. And then in a separate study, we looked at sleep deprivation, which is another common stressor that we have all experienced. We took subjects, and once again, I'm going to show you a dose response curves. Deviation from baseline again as a function of what the parameter is. Here is how many hours awake they are. Their normal wake time is time 0. They're awake for 16 hours, and then they go to their normal bedtime is at time 16. But here we don't let them go to bed, so they're basically kept up for 24 hours. And what you can see is really right after their standard bedtime. So if they wake up at 8 o'clock, right, then they go to bed at midnight, and at 1 in the morning, they're already showing deviations from their normal baseline. And what you can also see here is it's picking up not only the fact that folks are getting more fatigued, you also can see the sinusoidal modulation due to circadian rhythm, where your trough is somewhere around 4 in the morning, 4 or 5 in the morning here. And then you start to get better, even though you've been up longer. So you can pick up both the homeostatic sleepiness and the modulation caused by your circadian rhythms. And once again, these are not small effects, right? These are percent deviations from baseline, and we're seeing things in the double-digit percentages here. So that's another example of how things are changing. And I don't have the time to point this out, but the pattern effects across the 20 parameters that we measure is different for fatigue and sleep than it is for alcohol. And so there is specificity as well as great sensitivity to these measures. And the third one is a study that we're doing looking at-risk ophthalmology patients at Stanford who are on a drug regimen for a non-visual issue. that puts them at risk. And so they're being monitored by their ophthalmologist on a routine basis to make sure that they're not having retinal damage caused by the drug. And what we can see here is this is a group of normal. So this example is meant to show that we can do an across subject detection as well for people where we don't have a baseline. When you're a patient, you come in, you have an issue maybe, but you don't have a baseline necessarily. And what you can see here is this is the distribution of age-matched normals and the distribution of at-risk patients. And you can see a significant deviation between the two distributions. And I want to emphasize that these patients are all asymptomatic. They don't have any visual symptoms, and they're at risk of a problem. And only these two in red have been detected as actually having a retinal problem using standard state-of-the-art clinical techniques, which is OCT. And the others have not even been detected to have a problem. But what you can see is that as a population, they're clearly elevated with respect to age-matched controls. So this information is telling you that something may be going on very early with sensitivity that may even exceed state-of-the-art techniques that are being used in ophthalmology clinics around the world. One last thing is to show you that the physical link between these two. This is the latency, which is one of the 20 oculometrics. This is retinal thickness as measured by state-of-the-art OCT. And what you can see is a clear correlation across local retinal thickness measures and local responses to the oculomotor task that we have, showing you that the variation that we see in function is correlated with the variation in structure that folks have using state-of-the-art techniques related to a physically known location in their neural system, right? This is retinal data correlating with this latency change. So in conclusion, there are 20 metrics that we can derive in a 5-minute behavioral test that can be used to detect mild impairment associated with a wide range of stressors in slub or subclinical pathologies, folks that are at risk but not sick yet or not diagnosed yet. And so it could be used to both readiness to perform measures in aviation, space, military, and sports. How good are you on your own game? Are you at 80% or are you at 110 of your normal? So you can figure out whether you're ready to do something particularly difficult, or you can monitor your improvement if you're doing some kind of training regime. And also it could be used to support diagnostic decisions in neurology and ophthalmology. So, and with that, I am open for questions.
Great, thank you. That was very informative. So just 2 questions right now. The first one is, how long would it take for a private company or entrepreneur to set this up? And a question on the medical side, would the presence of glaucoma affect effectiveness of the methodology?
I'm going to answer the first question first, which is I have been talking to Dr. Leung at Stanford about doing a glaucoma study because I think COBRA has a strong potential to be able to pick up very, very early functional deficits caused by glaucoma. So that's a feature, not a bug. It would be able to, I think, detect things perhaps even sooner than standard state-of-the-art techniques. And as far as your first question, let's go back to this. What would you have to do if you wanted to commercialize this? You would have to, so this is about $1,000 worth of equipment when you just buy it off the shelf, right? $1,500. And you would have to be able to set up such a system and write the code to get this to work in real time and accurately, have your optics and everything else set up well. And then you would have to analyze the data in the way that we have shown works. So this is a very short lead time issue because you don't have to invent any new technology to get this to work. You just would have to figure out how to assemble this. And obviously, if you were buying these to make many, you could get much cheaper cost than when I had to build my. I have 3 of these set up: one at Stanford, one at JSC, and one at Ames. And as I said, it costs about $1,500 to build. My guess is you could lower that by an order of magnitude, and it would take 6 months to a year, and that would be perhaps even an exaggeration of how long it would take. If you have a team that knows how to work with programming and setting up visual display hardware and working with real-time data acquisition, it should be very straightforward and can be done very quickly.
Got it. Thank you. And then 2 final questions. First one is, would this methodology be possibly be applicable to diseases such as myasthenia gravis or Parkinson's? And the other one is, could it be used to treat depression and sleep disorders?
So I'm going to take the second question first again. It is not a therapeutic method, right? It doesn't treat things, right? But what it could be used is to monitor the effectiveness of treatments, right? So you could quantitatively measure how well someone's doing and then put them on a therapeutic regime and see whether it's working. And since we're talking about improving things subtly, you would have a very sensitive measure of whether or not your therapeutic technique works. So it could be used in conjunction with therapeutics to assist in that whole process. Now, as far as Parkinson's and what was the other one? Myasthenia gravis. Yes. Once again, what I would say is those diseases in their advanced stages have well-known oculomotor issues that are well-known along the lines of what I said as, traditional ways of using that, right? You can confirm things by seeing these, clear symptoms that occur. But what I would say is, while I have not done a Parkinson's study, clearly this technique could be used to look at very early Parkinson's and monitor the progress of the disease, right? And have a mechanism by which you would be able to see things before they get severe. So yes is the answer to that. And once again, I want to emphasize that the pattern across the different metrics may be different for these different diseases because the diseases manifest themselves in different parts of the brain.
Got it. Thank you so much. Appreciate it. That was a very informative presentation and very informative answer to the questions. Thank you.
All right. I'm going to say goodbye then. And I'm of course would be available to assist and help any licensee that we're working to apply this to any of these potential applications.
Great. Thank you. Appreciate that. Next up, we have Moana Guram, and they will be talking about their centralized data management platform technology. Moana, take it away.
Can you guys hear me?
Yes, we can hear you.
Oh, okay. Hey, everyone. My name is Mohana Guram. My background is in computer science, and I mostly work in the space of architecting and designing complex data systems. So today we're going to talk about this newly patented technology that we have worked in the past, that is centralized data management platform. This was intended to support multiple NASA missions, and it did support, as well as been supporting missions like EVA and Orion, to name a couple of them. So to give an overview, let me go to the next slide. To give an overview of this technology, the intent was to basically build a data system that can connect multiple data elements or data points from disparate data systems, because as you can imagine, data is being collected all over for specific context, but when it comes to decision making, you will need all that data from multiple sources, but there is no one technology that you can just plug in and should be able to give you all the answers, right? So that's one of the driving factor behind developing this system. So as part of this, the overall objective was to basically organically build a knowledge graph that can address queries in terms of how data is interconnected from multiple data sources kind of thing. So that was the internal objective, and that's what started this project. And as part of this, since the audience is more from the industry, I would like to focus on the application aspects of this. Before getting into that, let me give a brief overview of the diagram on the right side. As you can imagine, the data sources that come from multiple systems could be in different nature. For example, they could be tabular in nature, or they could be hierarchical in nature, and sometimes even graphical in nature, right? So that's why we had to build these microservices that would ingest that data and make those connections possible. So on the right side, you can see that there are microservices like metadata management systems, which is basically capturing metadata associated with various data assets. And we're going to talk about that a little bit more about what an asset means. The other one is the link management system, which is basically capturing all the interconnections between the data so that it can build a knowledge graph over time kind of thing. The other one is access control logic, which is kind of a key capability to control as to who get access to what kind of information and all that. The last one is more of the temporal management service, which is any data which is temporal in nature, so time-based data. So that was critical when we are dealing especially with data streams kind of thing. So the overall picture does give you an idea as to like it is capturing data in different formats and organizing it so that eventually it can build a knowledge graph within specific domain kind of thing. So when it comes to applications, let me take an example, a couple of applications that were built on this platform. The first one I would like to talk about is something called autonomous tracking and operations management. So basically ATOM, geeky name there. So the ATOM was basically built to manage hardware components of Orion spacecraft, basically. So you can imagine a spacecraft would have multiple hardware components with engineering diagrams, and each of these diagrams creating multiple instances of part. And you can imagine for test runs, there would be multiple set of parts that would be used, and they would be duplicated in other tests and stuff like that, right? So how do we organize that complex data, which is interconnected in nature, and there is always new information that is being produced, and how do we query all that information? And also, just to give an idea, like imagine a spacecraft that is being built and there are multiple entities involved, like contracting agencies building specific parts and everything. So information is flowing from every channel possible. Now, how do we organize all this data so that when we need to identify and query information with respect to specific part or a hierarchy of parts, how do we do that? So that was basically one of the applications that we built for Orion, and it was very well received, and it did help them really track down parts as well as identify documentations, especially like PRACAs, like problem reporting and corrective action systems kind of thing. Those documents, which are really critical to identify nature of problems associated with parts, even like shelf lives and stuff like that. So there is a lot of metadata associated with every part, and it is coming from different systems. Now, all those come together and can be visually presented. And we did end up actually presenting a visual model of a section of the spacecraft where we were driving the information as they were navigating the hardware components from a 3D visual point of view kind of thing. So that was really a cool product that we built on the platform. But at the end, it is the platform which is basically supporting all those features to be built within no time kind of thing. So that's one application. The other application is the Internet of Management things, right? This is to support ARMD and AOSP, Airspace Operations Safety Program, where you can imagine like management and leadership personnel making decisions in multiple meetings. They're having creating like meeting notes, and the information is lost in terms of where the decisions were made, what kind of decisions were made, who made the decision, what was the background behind that decision, and all that, right? This is very critical information in a product or a project life cycle. So in order to keep track of all this information, to interconnect all this data from these management decisions point of view, made be budget decisions, made be more of a milestone decision and stuff like that, right? How are they interconnected to each other? That was the product or the application that was built on the platform to manage these management decisions. The reason why we named it Internet of Management Things is because just like in Internet of Things, you can imagine sensors generating data continuously, and it's been accumulated in one place where they would visually make sense, kind of thing. So in the case of Internet of Management Things, we were tracking decisions made or the presentations made, as well as the milestones drafted and all the information within a project, or I would say a program also, to really connect all that information so that it could give a visual layout of who's making that decision, when was the decision made, and all that stuff. So basically the data provenance as to where that information came from, and the data lineage aspects as to like how that information was perceived and what did it influence that led to some other decisions that were made over time, kind of thing. So that was another product that we did build out of that. The other one I can give an example is Jay, please stop me when you know that it's time, kind of thing. So
Yeah,
just
you
go ahead.
got
Okay,
3 minutes.
all right. The other example that I can think of is basically the EVA mission, basically extravehicular activities. That is when an astronaut steps out of space station and does a maneuver of something, kind of thing. So as part of that, we have to, and the specific focus of the application that we were looking into was the spacesuit itself, as to like the components associated with the spacesuit, and if there were any problems that were reported in past. As you can imagine, there were some discrepancies in the operations that were performed by EVAs and all that. So collecting all that data from multiple data systems, having a history of every part that is being used for a specific mission, at least have that very handful of information available while executing the task, kind of thing. So that is another project that an application was built on the platform. And apart from this, there are many information retrieval projects, especially like one of the agencies, Tennis Research Center, basically they used it for their agency information to really just index their data for search and retrieval, kind of thing, and build knowledge graphs out of it, kind of thing. So that is the application space of the platform itself. And hopefully that will address some of the use cases that you guys are looking into. But it's a very generic platform that can be scaled to map information management or data management, knowledge management, data provenance, data lineage kind of use cases. So that's pretty much what I wanted to cover. I would be happy to take questions.
Yeah, thank you. That's very interesting. So while people type in their questions, um, so if somebody has like a team of software engineers, or even if they don't, how long would you think for either team it would take to kind of build up this system to integrate into their own?
Yeah. So I would say that it depends on the use case. First of all, the reason is setting up the infrastructure for this specific platform would not be that big of a deal, especially if there are familiar software engineers who are familiar with basically the technologies that are being referenced in the invention. I would say within a span of maybe 4 to 6 months, they should be able to set it up and be able to start test with some of the data sources that they have internally within their organization. But in order to scale it to real applications and everything, it may take at least 1 to 2 years to really see the product in a way that is mostly like can be called as an MVP kind of thing.
Got it. Interesting. We did get a question about how would we get access to the platform. That would be through licensing the technology, and I'll be going over how to license these technologies at the end of the webinar. And then we had another question, is that how does one, same question, how does one access or license a centralized data management platform? I'll be going over that at the end of the webinar. So thank you for your interest. Another question is, what is the benefits compared to what's out there in the current market compared to what you have here in the patent?
Yes, that's a very good question. The benefit that we note is not that we don't license out commercial products out there. We do license out commercial products for our own use. But one of the key benefit that we have really got out of the platform is the processes that are established within organizations, like especially NASA, are very tailored for specific needs. And a generic solution usually does not give us that flexibility to make those changes in terms of executing our own process methods. So that was one of the key benefits that we have seen in terms of using this platform for those non-generic use cases.
Got it. Interesting. And one final question before we move on to our next panelist is, could it be used to manage business data?
Yes, as I indicated, the Internet of Management Things was mostly business intelligence data, BI data, that was basically in terms of financial decisions, as well as project milestones, and even like task breakdown structures and stuff like that.
Got it. Thank you so much. Appreciate it. This was a very informative presentation. Thank you so much.
Yeah, thank you, everyone.
And next up, we have Robert Ma, and he will be talking about spacecraft with artificial gravity modules. Robert, take it away.
Hello, my name, like you said, is Robert Ma. I'm a research scientist at NASA Ames. This patent is about creating artificial gravity in space. As an aside, I worked on artificial gravity technology since 1975. This invention is a new way of creating artificial gravity that is different from rotating a large space station. Okay, this invention has a range of implementation configurations, but in the next 10 minutes, I will talk about only one of them. And if you're interested, we can arrange another meeting to go over the others. Okay, so in this implementation, there are two habitation modules. They move without friction on the large circular ring to create gravity, artificial gravity. These modules are 180 degrees apart for mass balancing. Each of the habitation module has thrusters to propel it and air bearings to provide a friction-free contact with the circular rail. So what happens is that with a short thruster pulse, it will cause the habitation module to move perpetually because there's no friction to slow it down. The circular rail will remain stationary because, as I said, the habitation module has no frictional contact with it. So what does this mean? This means there's also no need for a counter momentum wheel. So in the graphics, you see a schematic of the invention. I believe a prototype of this invention can be added to the ISS. The simplest configuration will be just two habitation modules and one circular rail that is hard mounted to the ISS. Later on, additional rails can be added when needed. For instance, one could be used for a service module to transport people, supplies, and perform maintenance. Another circular rail can be used to provide other gravitational levels like, either the moon, the Mars, or even Earth 1G. There is considerable interest in creating artificial gravity in space for a number of things. One is tourism, one is industrial use, scientific use, and also for countering the deterioration in health of space travel when they're on a long-duration mission, like to Mars and back. Next slide, please. Now, before this patent, like I said before, artificial gravity in space was envisioned to be a very large rotating space station. But the problem with large rotating space stations is that it has major engineering and safety issues. The mass imbalances, for instance, will cause gyroscopic motions and forces. And there's no zero G for research in space processing. And worst of all is the cost and the number of launches and schedule is prohibitive. For instance, for the 2001 Space Odyssey space station, it was estimated to cost $5 trillion, 18,382 launches to build it in space. Then there's the tethered module approach, but those have even more major engineering and safety issues. So in contrast, this new artificial gravity invention is practical and is cost effective. Each habitation module is mass balanced in real time to eliminate and reduce the gyroscopic forces and motion. And as I said before, you can add additional rails without disturbing the ongoing artificial gravity. And those other rails could be used for a service module or to create other artificial gravity levels. Can I have the next slide, please? Oh, I'm sorry, this is good. Can you go back, please? I'm sorry. Yeah, so what I show here is our examples of work that we did to demonstrate the feasibility of this invention. So the one on the right is the use of air bearings on guiding an human experiment platform without friction, and it's very smooth. There's no cues, there's just no vibration, just very smooth. I think we use as an actuator just the voice coil for something that like 300 pounds there. We also looked at use circular bearings you see on the right for centrifuge, and that just once you start the motion, it's almost perpetual. It's on Earth you have aerodynamic drag and dust on air bearings and that kind of stuff. Okay, on the lower left, just a depiction of using thrusters to propel the spacecraft prototype you see there. And these air bearings, they're 80 millionths of an inch flying height, and they use very little air. So the tanks you see there last for months for our research. And then on the right side is service modules. One of the challenges that if you have something rotating, you don't want to stop it to service it, because then you would be interfering with the gravity. So we came up with two designs. One is radial, is that the outer one is the rotating artificial gravity modules. The inner one is initially stationary. It spins up and matches the speed of the other one and does maintenance or transfer of habitat. So that's the same idea with this other circular rail that I talked about in the invention. The other approach we looked at was having the servicing perform in the axial direction. I don't think I have that picture there. And the last slide basically depicts our work on real-time mass balancing. So if you have an animal moving on the rotating device, you move counterweights in real time to maintain the center of gravity at the center of rotation. So the algorithm for that is available. So the whole thing, the whole system is mass balance in real time to minimize any disturbance to the artificial gravity. Anyway, that's the what I wanted to present. So are there any questions?
Great, thank you so much. That was very interesting. Kind of along the lines of, so while people type in their questions, what do you think maybe not so much cost be associated with setting something up like this, but like how long do you think it would take to kind of validate this in space? Would it just be trying to get a smaller sort of module on a rocket and test it out, or yeah, what do you think is kind of the best ways for companies to kind of look at this as a way for commercialization?
My recommendation is just build a small prototype on the ISS. You add a circular rail, and then the habitat could be something that you build, or you could use the Bigelow ones, which are self-sustaining, and use that. I mean, as a quick way to get humans on an artificial gravity. Ideally, what you want is a very large radius, but if you were to build a space station, that's just prohibitive. But with a circular rail, it's minimal structure, so it could be pretty large. But for validation, it's make one that's that would fit comfortably on the outside of the International Space Station.
Got it. Thank you. Got a question. It says, roughly how many sensors or what types of sensors might be used to monitor performance?
Well, what we have always used is load cells and accelerometer. The load cell measures the imbalance and allows us to correct for the mass that needs to be moved to counter it. We need encoders to know where the modules are. They should be 180 degrees to maintain balance. Accelerometer. Mostly, loads and motion sensors.
Yeah, that makes sense. And is there a scaling effect? So is there a dimensionally, is there a far end to how big it can be, or a short end of how small it can be?
Well, you look at human centrifuges that they try to fit in the ISS, so that's the smallest, but you have a lot of great gravity gradients. And optimally, you want something that's rotated at 1 or 2 RPM, and that could be, in diameter-wise, a couple of football field in diameter.
Okay.
So that's to minimize Coriolis effects. When you're on merry-go-round, you move your head, you feel these weird forces. That's what you need to minimize.
Got it. And we have one last question. It's asked is any reason not to simulate 1G?
No, I think you should, because part of it is to go to Mars and back. What level do you need to prevent the health deterioration? The analogy. I mean, what I think the research shows is that after months in space, you lose decades of bone. And then when you come back, it doesn't totally recover. So the analogy was the Eiffel Tower. If you have structural failure and you repair some of it, but not all of it, it could tip over. So can you survive that to Mars and back? That's a big question.
Good point. Well, thank you. That was very informative. And thank you for answering the questions as well. And next up, we have Nan Nguyen, and they'll be talking about real-time drag optimization control framework. Nan, take it away.
All right. Okay, so this invention is about a real-time drag optimization technology. So we can go to the next slide. Okay, so modern aircraft basically are moving toward a design with a thinner wing and high aspect ratio or longer wingspan for the purpose of increasing aerodynamic efficiency, which lead to reduced fuel consumption, which is the key driver to aircraft industry sustainable aviation and also, reducing the cost of air travel. And so these aircraft, modern aircraft like the 787 and the upcoming aircraft, the 777X, have a very long wingspans. You go to the next slide. So what happened when the wingspan increases? We call it high aspect ratio wing. Then these wing ships actually cannot maintain their ships in flight. They can only maintain the design ship at the design condition. But when you cruise off the design condition at like takeoff or landing, the wing ships changes drastically, and the ship changing wing can lead to non-optimal aerodynamic performance. So there is an aerodynamic performance penalty due to the changes in the wing shape. So the purpose of real-time drag optimization technology is really to provide a methodology to actively compensate for wing shape changes in flight. Next slide. So you can think of this like an adaptive wing technology. So if you have the ability to change the wing shape in flight throughout the flight envelope, then that wing shape is extremely efficient. It can minimize fuel burn consumption at all points in the flight in the flight envelope. So you can think of it more like a bio-inspired concept. And we know bird wings are highly adaptive because it changes shape continuously in flight. And this was a technology that we developed in the prior work, and we call it the variable camber continuous trailing edge flap system. And we actually work with Boeing on this technology and mature that technology. Next slide, please. And you can skip the next slide. I think it's we just don't have time, but it's just a little eye candy thing. So we're gonna go to the real-time drag optimization. So we think of the adaptive wing technology. You see that those conformal flap system. Think of it as like a body, and then you need the brain. So the brain is the real-time drag optimization. It provides the processing ability to tell the adaptive wing to reconfigure the wing at any point in the sky to minimize drag, hence fuel consumption. So the technology basically is about having onboard some sensor and also an onboard model. So it's really a sensor-driven technology, and the onboard model is continuously updated in real time by system identification process or model identification process. And so because the models, is updated in real time, then that eliminates the need for any validated math model for any offline optimization. Now, the current aircraft industry do use offline optimization. They have basically programmed in the FMS at aerodynamic databases, and then you can use table lookup and find out at what point in the sky we want to reprogram the control surfaces to move to certain deflection angles and to reduce drag. And here we eliminate the need to have that offline strategy because now the model is really updated in real time. And because of that, this technology is really applicable over a wide range of different aircraft configuration. So it doesn't matter if you have a Boeing 737 or a Boeing 787. If you apply this technology, then basically the technology can figure out what that model is for that particular aircraft or that specific aircraft, and then use that onboard model to come up with a strategy to reconfigure the wing surfaces to get better LVD or lift to drag ratio of fuel consumption. And so that's the basis of the technology. Next slide, please. So we did the validation of this technology in a wind tunnel test at the University of Washington probably 5-6 years ago. And we obtained basically 3.9% drag reduction in real time. And the figure on the right shows, all the actuators and all the microprocessor that drives the control surface in real time. And then please, next slide. If you could click on the figure on the right, or the image on the right, this is a video of the test that we did during that experiment. You can see the wing is kind of, it's pretty high aspect ratio wing, and then we have those sort of control surfaces in along the wing, and it goes through some periodic sampling, or we call it, excitation. It provides excitation input to the wing, and then there's measurement of lift and drag from the strain gauge balance, and then we collect the data and do basically onboard model identification, and then using that onboard model identification, we compute the necessary control surface deflection to seek a minimum drag solution from the onboard model. And that's basically, we did this test and it was fairly successful. And we have an upcoming test. Well, we're working with Boeing. We're going to do the same strategy with maybe with some further improvement. That test is coming up maybe in the next few months or so. And I think this is the last slide. So at this point, I'd like to open it up for any questions from the audience.
Yeah, thank you. That was very interesting. While we wait for questions, it's kind of similar to what I've asked everyone else. How long do you think it would take for a company to kind of integrate this into their systems, into the design of their wings and things like that?
So if the aircrafts already have control surfaces that are tailored to do this particular control, like a real-time drag control, then implementation of the algorithm in the software should not take that long, right? I mean, basically, the biggest time sink, in my opinion, is really having the ability to implement some sort of control actuator on an aircraft wing, because typically the conventional aircraft usually employ minimal control surfaces for flight control. Like you got aileron on the wing to do roll control, that's it. But in some of the modern aircraft, like the Boeing 787, they do implement additional control surfaces on the wing dedicated to like real-time cruise drag minimization. So if that technology, if those control surfaces are available, and you have some redundancy on the wing, then the implementation of the software is fairly straightforward. So it should not take that long, in my opinion.
Got it. Can this be used for smaller planes or even possibly drones that have control surfaces?
Yeah, absolutely. I mean, there's no reason why it would not be valid to a drone or anything. Some smaller aircraft like personal air vehicle or GA. The key is really having the control surfaces to enable this real-time drag optimization.
Got it. Another question we have is how are the mini flaps actuated? Is it by electrohydrostatic actuators? Will there be a significant weight hit?
Yeah, so that's a good question. In our work with Boeing, we actually explore ship member alloy. It has a highest torque to weight ratio. I mean, it produces a lot of torque to drive the flap, and it's pretty lightweight. The trade-off is that it's slow. It doesn't move very fast. So, but for real-time drag, that's not an issue because you don't really do any maneuver. As you cruise and as the aircraft cruises, then periodically the flap need to be adjusted, and the SMA should be able to take care of that.
Got it. Interesting. Thank you. I think that's it on the question side. Yeah, great. Thank you, Don. That was very informative. I appreciate it.
Okay.
And finally, I'll be going over how companies can or individuals can license NASA technology. Let me just share this. Can everyone see that?
Yes.
Great, thank you. So thank you again for everyone for joining. I'm just going to go over how to leverage NASA technology to benefit your ideas. So just wanted to give an overview of the NASA Technology Transfer Program. We have 10 different NASA centers all throughout the country. Here we're at NASA Ames Research Center in the San Francisco Bay Area. We have 3 different NASA centers in California, but you can see they're all spread out, some in the Midwest, some in the South, and some in the East Coast. As far as NASA Ames, our core competencies are intelligent adaptive systems. So that includes autonomy and robotics, human entry systems, things like that. Entry systems, advanced computing and IT systems, aerosciences, so testing on the ground before you take it to the sky, air traffic management, astrobiology and life science, as well as cost-effective space missions and space and earth science. Since its inception over 50 years ago, the NASA Technology Transfer Program, the main goal is to ensure innovations developed for exploration and discovery are brought to the public, maximizing the benefit to the nation. Whether you're looking to start a new company, enhance an existing product, or create a new product line using NASA technology can gain a competitive advantage in the marketplace because you're reducing time to market, you're using vetted, proven tech. You basically don't have to reinvent the wheel. And why would a company want to license NASA technology? I think that's a question that always gets asked. And a NASA license allows you access to technology for testing and to implement it into a system, a service, or product that can result in sales. The Ames Technology Transfer Office here in the Bay Area cares about the success of commercial businesses, and negotiation of terms is done by a case-by-case basis, which I'll be touching on that near the end of the slide. So here, I just wanted to touch on some spin-offs. So these are technologies that have been commercialized and put out into the real world. So on the left, we have anti-icing formulas to prevent train delays. So that was created to for de-icing space shuttle, and this was then created and used for using it on airplanes. You can see, like in cold weather climates, you'll see airplanes kind of being hosed down with material or liquid, and that's anti-icing formula, and as well as on train tracks. And then on the right, we have this mineral analyzer that what it does is it takes a sample of soil from wherever it might be. In this case, this was on the Mars Curiosity rover, which is sent, it was built in-house. And so it was sent to Mars, and what it does is it takes samples from the Martian surface, or anywhere else on Earth, and it could take a sample, put it in a X-ray diffraction machine. So what that does is it shakes the soil up very quickly, and it shoots X-rays through it, and you can see a diffraction pattern of what the minerals are, to see what the content of the soil or the rock is right then and there, rather than sending that sample back to the lab. So now I just wanted to briefly go over how companies can license the technology. So this is our main webpage, the technology.nasa.gov. And to search for the technology, you can either use the search bar, which is the magnifying glass icon on the right, or you can click on the NASA patent portfolio, and that's kind of how we'll step through it today. So once you click on the NASA patent portfolio, you'll be greeted by 15 different categories. Here we have things from communications, aerospace, instrumentation, optics, power generation, propulsion, robotics, things like that. NASA Ames has a technology in every category except propulsion. So for this instance, we'll step through the instrumentation category. So if you click on the instrumentation category, you'll be greeted with a web page similar to this, and there'll be a list of different technologies. Here, we'll click on the real-time radiation using nanotechnology technology, and if you go read more, you'll be greeted with this page. So here you have an overview of the technology on the left-hand side. So it's the overview of how it was created and what the use case was, and then the technology here shows on the bottom left-hand side what the technology does, and it's on the bottom right it has the benefits of the technology. And then if you keep going scrolling down on the web page, you'll see the applications of where it can work. And if you have any questions about that technology, feel free to click on the questions tab. And if you want to download a fact sheet, just feel free to go to download fact sheet as a PDF, and you'll be greeted with this, which is similar to what you would see on the web page, but you can, this is easily shareable, or you can download it and send it to others. It also shows the publications, which here it shows the patent number. And the patent is the most important part of reading the technologies, because the patent will show the claims and the description, and that's what you're going to be licensing. So what it claims to be doing and the description of the invention. So those two things are very important to read before you apply for a license or ask questions. And so if you're interested in learning more on how to license technology, you can go to technology.nasa.gov, and you can click on how to license, and it'll give you information on the different types of licenses, the evaluation license, commercial license, and a startup license. And then if you're ready to apply for a license, you can just click on the apply to license technology. And just wanted to reaffirm that your company must be legally formed in the United States in order to apply for a license. So after you click on the apply to license link, you are then greeted by our automated technology licensing application system, which is called Atlas. And once your account is created, the license application page should be open, and from there you are able to apply for the license and give information of why you're using it, your use cases, and things like that. And the more information, the better. That allows for our licensing managers to better understand your use case, better vet your application. So the more information you have on how your use case is, the better. And these are just an overview of our agreement types. So we have an evaluation license, a startup license, and a commercial license. So an evaluation license offers an option for using the technology for a short-term basis to kind of explore the potential of the technology and learn if it fit in your business development goals. An evaluation license is also required if you intend to enter into agreement to have NASA conduct testing on the technology on your behalf. This is a great way to kind of test drive the technology, kind of kick the wheel, see if it works. During this evaluation license, you are not able to commercialize the technology, but if you'd like to commercialize technology, you can go into a commercial license, which is a standard commercial license. And while NASA offers a standard licensing template, each can be negotiated on a case-by-case basis, and as well as a startup license. So by offering a license, a startup license is for startup companies who I believe are newly formed in the last year, and companies can take the technology with no upfront costs, and can kind of run with it and see how it works with their systems, their technology, their product plan, and you don't pay royalties for the first 3 years or until you make your first sale on the technology. And all of these require a full business plan, marketing plan, tech development plan, which will allow the NASA technology transfer team to understand your use case and see if the technology fits what you need it to use. In terms of cost, commercial licenses are done by case-by-case basis, and the evaluation license depends on the technology and the use case and the length of the evaluation license. And evaluation licenses can go from anywhere from 6 months to a year. So that it all is a case-by-case basis. The technology.nasa.gov/license web link can provide more information on that. And here is the NASA software catalog. So this is a program that we have where individuals, companies, entrepreneurs, folks in academia can use NASA software for free. So we have many different categories ranging from aeronautics to propulsion, vehicle management, materials and processes, things like that. And we have 3 different release types. The first one is government purpose release type. So for this, you would need a government contract. So what that means is you're doing work for the government in a specific area, and that technology is needed for you to complete that work. And then you have general purpose. So there's 3 different categories in general purpose. So it's US only, so you'd have to be based in the United States. You have US and foreign, so that is open to other countries as well. And then public, which is open to the public. And then we also have open source technology at code.nasa.gov. And it's just a caveat that for the technologies that require software usage agreement, so everything other than open source technology, if you want to integrate it into your code and commercialize it, you'd have to license the technology. If you're just looking at seeing how to test things and everything like that, you can just sign a software usage agreement. And here are just some quick links for the program. We have technology.nasa.gov, where we have all our information, our NASA patents, our free software, success stories, so those are spin-offs, and you have my contact information, and Kim Hines, who is the chief of the Technology Transfer Office, her information down below.